Hello! In this video, we are going to learn more details about how to use the geometry merger. For this video, it is assumed that you, the viewer, have learned what the geometry merger does and now wish to learn more about how to use it. Looking at the merger command dialog again, there are not many settings, and because they are saved across command invocations and AutoCAD sessions, you will not have to modify them often. Let's see what they all do. We will start with the Merge What option. It's a radial button. You only have two choices. The merger was intended to be used on entire drawings all at once, so that is the recommended option. However, Select Objects is a powerful alternative and allows you to run the merger with different settings on different sets of objects. Anonymous blocks can only be reached with the Everything option, and the merger does not process XREFs directly. However, you can edit them under RefEdit if you really want. The target geometry level is another multiple choice option, this time with 3 choices. The term level is used because each of the last 2 options does everything that the prior option does, then adds another level of processing. Behind the cleaner and prettier models that the merger produces, there is a lot of computation going on. Internally, the sub-D meshes processing happens first, and then the surfaces and solids processing is performed, and finally the create profile entities phase is performed as requested. The text on this slide is detailed and doesn't really bear repeating, so just pause the video until you are done reading and ready to move on. Next, let's look at the log file options. There's 2 options. You have a checkbox to indicate whether you want a log file or not, and a field to enter the name. Earlier, we stated that all merger settings are saved between commands and sessions. Well, the log file name is the exception. We assume that if you do want the log file, that you would like it to be easy to find and with a name that makes sense, so that's what we do. Which brings us to the question, when and why would you want the log file? It isn't required to perform the merge, but it comes in handy if you want to know what the merger did at a high level. We'll be looking at log file constants later to understand how the tolerance settings work. Let's go over what the 3 buttons along the bottom do next. Restore defaults and perform merge are self-explanatory. Cancel does what it says, but is a little unusual in that it will keep setting changes that you made. This is done to allow you to use the dialog once to establish a settings baseline, and then run the command again to perform the merge and then undo back to the baseline settings. Undoing a merger command undoes the setting changes made in the command. And if the command encounters an internal error, which is rare but happens, changes made in that invocation are reverted because extreme settings often lead to internal errors. Okay, that leaves the tolerances and rules section of the dialog. Let's learn more about these control knobs and how to adapt them for your models. This slide is a review of the merger process described in the introductory video for the purpose of illustrating where the tolerance settings and strip caps rule have their effect. Notice that the point equality tolerance is the most important control because it influences all phases of the merge operation. The other tolerances and the strip caps option are applied only when attempting to fit mesh profiles for higher order geometry. So where does all this low precision data come from? A number of sources, typically external to AutoCAD, which has always stored double precision data. 3D faces are common because they're easier to program and have been around a long time. So there's a lot of examples out there, and drawing DWG export programs often rely upon them. So configurable tolerancing is the key to the merger's capability. Next, we'll explore how to find the best tolerance settings for your model. Good tolerance settings eliminate the noise, but not the significant model detail. We are now going to spend the next several minutes discussing the point equality distance tolerance. It is the most complex subject we will cover, but it is important to have an understanding of. The good news is that all the remaining settings are simple and will go quickly. When discussing distance equality tolerance, bear in mind that AutoCAD has its own internal tolerance settings, which are not under user control. And which settings are used in any given feature or command vary due to disparate tolerance needs and independently developed subsystems. This slide shows a set of recommended tolerance value ranges. Notice that there are values which are fixed in magnitude and size, and others which are scaled to coordinate magnitude, which is typically represented by the length of the model extents diagonal. It is better to try to accommodate both the absolute tolerance ranges and the extents scaled tolerance ranges when using the merger. If your model coordinates are outside the recommended ranges and the merger doesn't work well, you can always try it first. Consider scaling your model to fit before running the merger, and then scaling it back to its original size afterwards. Before we show what different tolerance values do, it is a good time to look at a key section of the log file where their effects are shown. Here is what a log file looks like in Notepad, and it's actually displayed at the top of the file so you can see where the key section is, and it's not far from the top. The number of points merged due to tolerance and the number of face edges collapsed represents the effect of the point distance tolerance value on the given model. As the tolerance value is increased for a given model, eventually go up. Also, the count of usable faces and degenerate faces is an interesting set of numbers to keep an eye on, although they can rise when the face edge collapses rise. In this case, we had a lot more duplicates, so there was really just dirty data in there. The number of contiguity groups indicates the number of the model, and the face normal reversals are done to give each mesh a consistent front side for one-sided rendering. To help determine what range of tolerance values will work for a given model, there is a line in the log file which gives you the smallest non-zero distance between any pair of points in the model, which is also the smallest tolerance value that would have any effect in merging points for that model. Just run the merger once on your original model to find this value. And some models have data that is all good full double precision data. For example, this model has data points that are either exactly equal or substantially spaced. No point merging is necessary for this model. In that case, you still want to set the point tolerance to a value where the geometric fit multiplier will have a relevant value. We'll visit that setting in greater detail later. The model we are using is really 5 different sets of faces taken from the same real-world model. So let's run the command already. Oh, we see that the dialog box does do range checking on your tolerance setting values, but they're just warnings, so we're going to run it anyway. It's safe to ignore the warnings. So, what did we get? Looking at the log file, we see that the small point distance tolerance caused the merger to leave all the original data points. Only one duplicate face, pretty clean data actually. But notice that we found 15 meshes rather than the 5 that we were hoping for. Now, looking at the model results, we see that the set of faces on the right became a network surface, and the next set of faces over became a single mesh. So, because the merger left all the points intact, it is apparent that both of these face sets were computed in double precision and all their adjacent faces had exactly equal vertex points. The 3 apparent forms on the left, on the other hand, did not fare quite so smoothly. If we look at the apparent sweep, we actually see that it's a few meshes, actually 4 of them. And the apparent revolution, or wheel here, is a mesh, so we think we can do better there. And this final piece up here is actually all kinds of little pieces, and you can see that even though they look like they should be a surface, they aren't, so there's probably data noise there. And oh, down here we do have a network. And let's not forget that, because this mesh will eventually be merged into a single piece that cannot be promoted. So let's just say that when you see something like this at a small level that works out, you may want to export it. Or you can come back and revisit it later on after you've marched your way up through the tolerance ranges that you want to explore. Before we move on, I'm just going to bring up the dialog box again, just to show that it will issue warnings for extreme setting values still in effect. AutoCAD will often set values smaller than 1.0 e to the minus 10 to 0 because they are equivalent by AutoCAD tolerance. Now that we have seen what happens with this tolerance, let's back up and try the next tolerance setting. At this point, undo is going to be one of your best friends. Now let's run the merger using 1e minus 10 for the distance tolerance. If you are in doubt about your model's data precision, this is the best value to start with because it is a typical tolerance used by AutoCAD, especially in the solid and surface modeling code. Looking at this runs log file, we see how this tolerance value is already causing points to be merged. And we also have more duplicate faces, and now we're down to about 12 meshes where we were hoping for 5. Looking at the model again, we now see that the apparent sweep is still in fragments, although fewer. But look, the apparent revolution is now really a revolution. So the higher tolerance value was better for it. And the other form is still in several pieces. And notice that the network surface we had at the bottom, for the bottom set of faces, is now just a mesh. So the higher tolerance ruined its regular M by N face pattern that it had. So it really was a double precision object. And these other pieces are, yep, they're all still different things. Actually, they're becoming surfaces now, but there's still too many pieces, and we want to fix that too. One more thing about the bottom side mesh is that it appears to be all in a single plane, for which there is another possible promotion path, which we will cover later. At this point, a smart thing to do would be to zoom in on the boundaries of the disjoint meshes and see if we can get a feel for the kind of gap distances we still have. This is best done with the original data, since point merging shifts the points. Okay, let's zoom in and see what we have. Ooh, look at that. Starting to see some daylight here. Oh my God, look at this. Look at these gaps. The gaps are so big that AutoCAD easily dimensions them. When you see a gap like this, try setting the point tolerance to about 3 to 4 times bigger than the size of the gaps you find. So we'll try 0.0004 for the next point equality tolerance. Looking at this merge log and comparing with the log from the 1e minus 10 tolerance setting, we see that we have merged more points, but we have no additional face collapses nor additional duplicates. In other words, even by increasing it by over 1,000, we are still eliminating data noise without losing model detail. Looking at the model, we now see that the remaining apparent forms are now both single meshes. They are not the sweep and loft that we were looking for, so let's look for gaps again. Here is a gap that I found in the apparent sweep, almost 2/1000th of a drawing unit. So now let's try 0.004 as the tolerance. And finally, we have a sweep. Looking at the log, we see that even more point merges have occurred, but no new face edge collapses or duplicates or degenerate geometry. So we're still not losing any model detail, but we are coalescing the model detail that was probably intended. But the apparent loft is still a mesh. And eventually we discovered that the bottom plane mesh was just not well aligned with the side faces. We'll come back to that. That said, let's move on through the bigger tolerances now. Let's try 0.04 this time. Looking at the log again, we see that things are starting to degrade. We have more merged points, but now the number of collapsed face edges and the number of degenerate faces is increasing dramatically from the expected number. Also, the number of contiguity groups has gone from the expected number of 5 back up to 13. So we're not headed in a good direction anymore. And we'll take one last look at the drawing, and we see that the revolution is now a mesh again, because too much of its model detail has been lost. But because this is a learning video, let's see what happens when we push the tolerance up yet another 10x. With this tolerance, we lose more points than we keep, and we're losing about a third of the faces to degeneracy, and we have way too many contiguity groups or meshes anymore. It is becoming obvious that there is no point in increasing the point tolerance any further. Notice that all the apparent forms have now lost all useful detail. And so by now, we have been through the useful tolerance range for this model, and 3 of the 5 forms promoted to higher order geometry, all at the 0.004 distance tolerance. The second form on the right remained a mesh at all levels due to irregular rows and columns. So what about the irregular form on the left? Well, it became a single mesh at the 0.004 setting, but we think we can do better. Let's try isolating its pieces. If you recall, the bottom face became a network surface at the 1e-17 tolerance, so we're going to run the merger with that value, and this time we will stop at creating meshes so that we can then segregate them, explode them, and remerge them using different tolerance settings. So now I have just W-blocked the bottom side mesh to a separate drawing and then erased it from this model. The remaining meshes must all be re-exploded back into faces so that they can be merged at a higher tolerance. Let's try converting what is left at the default distance tolerance. And now we have a nice loft. Looks pretty smooth, huh? Looking at the isolated bottom mesh, if we merged it with the tolerance of 1e-17, we would get the network surface that we previously saw. However, if we merge it with a tolerance of 0.04, we get a promotion by another route, which is that all meshes whose points are in a plane will be promoted to a thin extrusion of the outline of the mesh. Insert a merged bottom side drawing back in, and there we have it. Finally, that wraps up our discussion of the merger workflow for a difficult model. Now we have only a couple of shorter and easier topics to go in this video. So that is what the fit tolerance does. Notice the recommended ranges here, although you should feel free to experiment. The remaining tolerances and rules are only used when analyzing mesh point data for extracting surfaces and solids from meshes. The geometric fit tolerance is used when fitting data points to curves and planes. Furthermore, the merging of points will introduce data error, for which the geometric fit tolerance compensates. The fit tolerance is presented as a multiple of the point distance tolerance because the fit tolerance tends to scale along with it. Which brings us to an important detail. If you have the point distance equality tolerance set to 0.0 in search of good double precision data, and you want to extract surfaces and solids, you should now set it to a non-zero value with 1e-10 recommended as the AutoCAD default precision value. Let's take a look before finishing this slide. We start with an idealized circle, which a set of points has defined from their centroid and their average distance from that centroid. Now we see some sample profile data points, which are visually different from, but still close to the circle. Some of the imprecision is inherent in the data, and the point merge phase introduced a bit more error. So what makes it a circle? The geometric fit tolerance. That's what. Now we see the region defined by the curve and the geometric fit tolerance, which together define the region bordered in green. The point distance tolerance of 0.004 and a geometric fit multiplier of 12 yield the resulting fit tolerance of 0.048. And the sample profile points all fit within the geometric tolerance region, so this profile will be represented as a circle. Now, let's run the merger on this sample frame with all the default settings, except that we will collect the parameter profiles for inspection later. And we end up with a nice loft surface, which is kind of what we expected. By hiding the loft and looking at its defining profiles, we see that most of the profiles are circles, and most of them are the same diameter. However, the tube is deformed at the turns, it turns out, and so instead of just circles, we have an ellipse and some spline polylines. And it is a loft with many profiles, so it has a big footprint in memory and on disk. Looking at these three superimposed profiles, we see that the ellipse and the spline are not quite within the range of the geometric fit tolerance, although they are rather close. If we increase the geometry fit multiplier to about 20 and run the merge again, this time we'll end up with a sweep of a circle. One look at the profiles indicates why the sweeps will typically consume much less space than a corresponding loft will. 2 parameter profiles are used instead of dozens for the loft. In this case, the sweep is about 25% the footprint consumed by the loft, and it looks at least as good. The angle tolerance value has a rather narrow scope of usage compared to the geometric fit tolerance, but it is related. It is used when comparing the starting and ending angles of different arcs for equivalence. In this set of faces, the merger will find the unclosed arc profiles wrapping from one edge of this potential revolution to the other. If the start and end angles of each profile are not within the angle tolerance of each other, then it would not be a revolution. But it is. Again, based on observed data, the default value is much larger than AutoCAD's default angle tolerance. You probably won't be changing the setting often, but it is there if you need it. And finally, the checkbox option you're probably wondering about. Stripping cap faces from a mesh during profile analysis will allow some meshes with non-radial cap faces to become viable solid surface candidates. It's easier to show than explain, so let's just look. Here is a mesh with regular M by N profiles. Notice that its ends have no cap faces on them, so the sweep will be found regardless of the strip cap setting. Like so. Now let's look at a similar set of faces, which also appear like they're destined to be a sweep. But notice that it has faces covering its apparent cap. They look nice, but with cap faces disabled, these faces will convert to a mesh. So let's run it again with the strip caps option enabled. And by ignoring the cap faces, this form now becomes a sweep. True, the cap faces are gone, but if you collect the parameter profiles, you can use them to form regions or whatever kind of cap you wish. Now, let's look at a model where stripping caps should be disabled. Here's a set of faces representing a stove burner set. It looks nice and solid when shaded. So let's run the merger without stripping caps. And it ends up being a series of meshes, but it still looks about the same as the original set of faces. Now let's run the merger with cap stripping enabled. Now when we look, we see that we have a lot of surfaces and solids. But if we zoom in now, we'll see that without the missing stripped caps, the results are not nearly as good. Wow, that was a long video with a lot of details. Thank you for enduring it all and watching this far. The merger will come with a small document which offers more details on how it works and known issues and problems. Thank you again for watching.